we were working on example finding the area under f of x equals sine x over the interval 0 to 2 pi. And when we did our calculations, we did area equals 0 to 2 pi sine x dx. That came out as 0. And then we were thinking that why the area is coming out as 0. So let's see if I graph it here. We have the graph of sine from 0 to 2 pi, given as it has a hump going up here, then it goes down. This is 3 pi over 2, and then it comes back to 2 pi here. This is equal to pi. This would be pi over 2, and this value is 3 pi over 2. So you see that we have this positive area. Our function is always positive. But as we go through x equals to pi, the function goes negative. I wouldn't call it negative area, but the Riemann sum will have a negative value. And it's exactly the same as the orange one in terms of its absolute value. So they cancel out and we get a value of 0. To get the total area that is enclosed by sine x and the x-axis from 0 to 2 pi, what I need to do here is I need to write area as this integral 0 to 2 pi sine x dx, but I have to split it. Equals, first I go from 0 to pi. I know this is going to have a positive value, sine x dx. And then when I go from pi to 2 pi, I use an absolute value. 0, pi to 2 pi sine of x dx. Because I know in this range of angle, pi to 2 pi, my function goes under the x-axis. My Riemann sum is going to come out as negative. To find the area, I have to take the absolute value. Now let's proceed. Let's evaluate this. This equals negative cos x. This is the antiderivative. We go from 0 to pi. And then plus the absolute value. Again, this is cos x with negative sign. And our x goes from pi up to 2 pi. I close the absolute value here. Now using the fundamental theorem, this is negative. Let's put the negative sign outside. Negative. It's cos of pi negative cos of 0, the antiderivative at the upper limit, minus the antiderivative at the lower limit, plus the absolute value. That would take care of the negative sign, cosine 2 pi negative cosine of pi. And then the absolute value stays there. This now becomes negative. Cos of pi is negative 1. Cos of 0 is equal to 1. Plus the absolute value, cos of 2 pi is 1. Negative cos of pi, this is negative 1. Absolute value has already turned it into positive. Now we can remove that. This equals negative 2 plus 1 plus 1. That's also 2. So 2 plus 2, we get now a non-zero value for the area, which is equal to 4. Okay, so it's this term which was canceling out this term over here. That's why we got the value as 0 in this case. Another example, a similar example. Find the area, the total area, bounded by the graph of the function f of x equals x cubed negative x squared, negative 2x, and the x-axis over the interval -1 up to 2. Now, because I'm looking for the total area, I have to be very careful. I need to see where my function goes negative, and I need to see where my function goes positive. Let's try to sketch this. It's a cubic function, so it'll have the general shape of a cubic function. What I can do to simplify my work is find zeros of this function. Notice our f of x equals, I can factor out 1x, and then it's x squared negative x negative 2. And I can factorize the term in the brackets. This is x. The factors for these are x plus 1, x minus 2. Therefore, now f of x equals to 0 will imply x equals to -1, x equals to 0, and x equals to plus 2. I have found all three zeros of this cubic function. So we know it's going to go through the x-axis here. It's going to touch the x-axis over here, and it has a 0 at this point as well. This is the value 1 in the middle. And you see that for this function here, when my x goes to infinity, because my leading term is x cubed, I know the function is going to go to infinity as well. And when my limit goes to -infinity, because my leading term is x cubed, it's going to keep the negative sign. My function goes to -infinity. Okay, now I can roughly sketch it. It's a cubic function. It goes to infinity here. When x goes to infinity, crosses the x-axis, crosses at the origin, and then crosses at this 0, and then goes down to -infinity. Using that, the fact that this is the general shape of the cubic functions. Once I do this, I see that I have this positive area here that is bounded by the graph. This is -1, this is 2. And then I have this negative value coming from the region 0 to 2. So when I calculate the integral from 0 to 2, I need to use the absolute value. I would write total area is given by, now normally we would write the integral -1 to 2, the function f of x dx, but we know in this case we have to split it. We have to write this. For the orange area, we write -1 to 0, our function f of x dx. We know this is going to be positive, no need of an absolute value, but plus 0 to 2, this must come with an absolute value, our function f of x dx, because we know this is going to turn negative. Now let's proceed. Let's do the integrals. This equals -1 to 0. Our function was x cubed negative x squared negative 2x dx, and then plus absolute value 0 to 2 x cubed negative x squared negative 2x dx. Now I do the antiderivative using the power rule. This will give me, first term gives me x cubed over 3. Sorry, my bad. Adding 1, so 4 over 4. Negative, this is x3 over 3, second term. Negative, this gives me 2x to the 2 divided by 2, and my x goes from -1 up to 0. Similarly here, the antiderivative is the same. X to the 4 divided by 4, x to the 3 divided by 3, 2x squared divided by 2, x equals, in this case, 0, and goes up to plus 2. Now you see that my upper limit is 0, and every term in my antiderivative has an x in it. So at the upper limit, everything is 0. It's going to be 0. This is my antiderivative at the upper limit. minus my antiderivative at x equals to -1. So -1 to the 4 divided by 4, -1 to the 3 divided by 3, negative -1 squared, and this is my orange area that we shaded right here. Now for the green part, you see that my lower limit is 0, and every term in the antiderivative has an x. So it's going to be 0 at x equals to 0. I would simply write absolute value 2 to the 4 divided by 4, 2 to the 3 divided by 3, negative 2's cross out, 2 squared. This is my antiderivative at the upper limit. I know at the lower limit, everything is 0, and then the absolute value. Now, when you simplify, when you add them together, it all sums to, in the end, 37 divided by 12. And it's the total area, the green part, the green shaded part right here, and plus the orange part. And that's what we want. Okay, now let's move to 5.5, where we go through the method of substitution for the evaluation of indefinite integrals. Let me write the statement. It makes more sense when we start doing examples on it. But let's state it first. The method of substitution. This states that if u equals a function of x is a differentiable function whose range, let's say, is an interval I, and if f is continuous on I, then, now you will see how f and g are related. The indefinite integral of f composed with g of x, which is multiplied by g prime of x dx, this equals the integral of f of u du. Let me write an example, and you'll see what it exactly means then. Suppose we are doing this indefinite integral of 2x e to the x squared dx. Now you see, this is not a standard integral, and we haven't done that before. When we were doing our antiderivatives, it was not in the list at that time. So I'm going to simplify it. I'm going to try to reduce it to something that I already know. The integral of sine, cosine, exponential, logarithmic, or anything that I have seen before. I make a substitution to do so. I take u equals x squared. This is my substitution. Substituting. And this is this part here. U equals g of x. And we said g should be differentiable. And the reason for that is I am changing my variable of integration. I am going from x variable to a u variable. Now I have to rewrite this whole integral in blue with only u in it. I should not see any x in it. That means I have to change my dx, I have to change my exponential function, and I have to take care of this 2x term as well. Let's see, how can we do this? If you remember from differentials, we wrote if y equals f of x, then dy equals the derivative of f with respect to x times dx. I'm going to apply this here. Du equals the derivative with respect to x of the function on the right-hand side multiplied by dx, which gives me du equals 2x dx. Now that is great because I can pair this 2x with dx, and I know this whole thing is going to become du. Let's rewrite this integral now in our new variable. 2x e to the x squared dx. This now becomes 2x dx is my du. I write this over here. And I have chosen u equals 2x squared in my substitution. This makes exponential term as e to the u. This is that part right here. We got an integral only in u, which we should be able to evaluate. The question at this stage is, what is the function whose derivative is e to the u with respect to u? That's the key here, that we have reduced to a function of u now. And we know the function has to be e to the u itself. This equals, from antiderivatives, e to the u plus the constant of integration. Now we are doing indefinite integrals. We must put plus c at the end. But we're not done yet, because our original variable is not u. Our original variable is x. Now I go back to my substitution. I know u equals to x squared. I finally write, this is e x squared plus the constant of integration. That is the antiderivative for this function over here. Now we are done with the indefinite integral. So here, this is the process. In general, summary, if you are given an integral of the form f of g of x times g prime x dx, what you do is you first write u equals g of x. You choose the substitution. So substitute this. Then you calculate the differential, which will imply du equals dg dx times dx. You use this differential. This is your step 2. Now rewrite the integral in only u variable. You should not see any x when you rewrite your integral. Integrate, once you have done this, with respect to u. But at the end, don't forget, replace u by g of x. This is the general procedure that you do for substitution. Another example. Let's take the indefinite integral tan inverse of x divided by 1 plus x squared dx. Now, once again, you can see that it's not a standard function. We do not know the indefinite integral or the antiderivative of this directly. So now I choose a substitution. I am going to choose, and we'll talk about that in a minute. Why do we choose this? I choose u equals, let u equals tan inverse of the variable x. Once I have made my substitution, I do the differential. du equals d over dx tangent inverse of x dx. The derivative of tan inverse is 1 over 1 plus x squared multiplied by dx. Super. When I see my integral now and try to rewrite it, tan inverse of x 1 plus x squared dx, I can pair 1 over 1 plus x squared with dx and replace this whole thing by du. So this becomes du. I have chosen tan inverse of x to be equal to u. Now this is a simple integral of u with respect to u. I can apply the power rule. It's u to the 1, the power rule that we wrote for antiderivatives. This is u 1 plus 1 divided by 1 plus 1 plus c, which is u squared divided by 2 plus c. But remember, we're not done yet. We have to go back to our substitution, our original variable. U equals tan inverse of x. So finally, I would write now, this is tan inverse of x squared, all divided by 2 plus the constant of integration. That would be our final answer. Now the question would be, how do we pick the substitution? How do we know which function to use for substitution? And at this stage, at least at the start here, we can say that, for example, when I look at this integral here, there are two possibilities. Either I take u equals to tan inverse of x, or I take u equals to 1 plus x squared to simplify my work. When I take the derivative of 1 plus x squared, I don't get tan inverse of x. But when I take the derivative of tan inverse of x, I am getting 1 plus x squared. So I know that taking a substitution of u equals to tan inverse of x might simplify my integral. There is part of the integrand whose derivative is sitting inside the integral, which is tan inverse of x in this case. And I go for that substitution. So at this stage, in summary, you can make a rule for yourself that you would go for the substitution for the part of the integrand if its derivative is sitting inside the integral. Even if you're off by a constant, a multiplicative constant, we can always adjust for that, and I'll show you examples on that. But as long as you get all the expression in x, you are good to apply that substitution. Let's do more examples on it. Now suppose I have integral log natural of x times 1 over x dx. Now you see, when we look at this integrand ln of x times 1 over x, the derivative of ln x is 1 over x. It's inside my integral. So it's all set for substitution. I would go ahead and write, let u equals this function ln of x, because I already have its derivative in the integral. It might simplify my work. Okay, let's do the differential. Du d over dx ln of x times dx. This gives us du equals 1 over x dx. Wonderful. When I rewrite my integral, ln of x times 1 over x dx, this becomes the integral. Ln of x is chosen as u. 1 over x dx has become our du. I have rewritten my integral completely in terms of u now, which is great sign. Okay, now once again, this is u squared over 2 plus c. It's the integral with respect to u. Now I go back to my substitution. U equals ln of x. This must be ln of x whole squared divided by 2 plus the constant of integration. Sweet. Another example. Suppose we have the indefinite integral sine 4x cos x dx. Now I have two choices here. I can take u equals to cos x and I can take u equals to sine x, and both are derivatives of each other. The derivative of cos is negative sine, but we can always adjust for any constant that is multiplied with the derivative. Now, first, I will take u equals to cos x and show you why that might not be the best substitution here. We can still work it out, but maybe the other one would be more appropriate. So let's do that first. Let's take u, let u equals cos x. Its derivative is sine x, and I do have a sine x in my integral. So du becomes negative sine x dx, or I can write -1 times du equals sine x dx. Great. Now I go to my integral. I write sine cubed x cos x, and I take off one of the signs and gel it with dx here. With this, I can write sine cubed x. Cos x was chosen as u. Sine x dx is negative du, -1 du. Now I still have sine in my integral, and it is sine of x. I cannot leave an x there. But luckily, I have this identity, cos squared x plus sine squared x equals to 1, and sine x equals 1 minus cos squared x, 1/2. I am calculating sine cube of x. It'll give me sine cube x equals 1 minus cos squared x to the power 3/2. And because my u equals cos x, I can write that this is equal to 1 minus u squared to the power 3/2. That's great. My integral becomes 1 minus u squared 3/2 times u. I had a negative sign, I put it outside, du. This is what the integral becomes. Now at this stage, I actually don't know how to compute that. I might need one more substitution to simplify that further. So we made a substitution u equals to cos x, we transformed everything. It leads us to an integral where we might need one more substitution. So I'm going to leave it here, and you will be able to do it later on. But let's go with the other substitution. Let's go with the other choice. I take u equals to sine x this time. This is the thing with the substitutions. You try one. If it simplifies your integral, that's great. You keep going. But if it doesn't, you go back and try a different substitution. Now I take u equals to sine x. This gives me du equals d/dx of sine x times dx. This is cos x dx. Wonderful. Now I rewrite my integral. Sine 4x cos x dx. Sine is chosen as u to the 4. Cos x dx is du, which is a simple integral, u to the 5 divided by 5 plus c. And u is sine. This finally becomes sine 5x divided by 5 plus c. It's much simpler than the one that we did with u equals to cos x. But we can still do that one, but not at this stage. Okay. And always remember that even with the substitutions, sometimes you will apply a substitution that will not work at all. It'll even complicate your integral further. So again, you just go back and apply a different substitution. And also, the substitution is not a unique substitution. You might find your answer using a different substitution than what I do. But the answer must not change. The answer has to be the same. The substitutions can be different in different cases. Or even for the same integral, they can be different. Okay, now I take another example. The indefinite integral of secant x squared tangent x squared 2x dx. Now, there are quite a lot of different ways in which we can do that. But I'll start with let x squared u equals, x squared. And the reason for that is because I see that 2x is sitting inside the integral. So that might simplify my work. This gives me du equals d over dx of x squared multiplied with dx. Well, 5.5 is definitely on the final. All of it. Okay, this implies du equals 2x times dx. When I rewrite my integral, secant x squared tangent x squared 2x dx, this becomes secant u tangent u 2x dx is du. Now the question would be, what is the function whose derivative is secant u times tan u with respect to u? And we know that the function is secant u. So this equals secant u plus c. With u equals to x squared, my integral finally becomes secant x squared plus the constant of integration. Okay. Let's take another one. Before I write another example, I'll try something different just to make a point that a substitution is not something unique. You may make a different substitution and get the same answer. So let's do it here on the side. I will now take instead u equals to secant of x squared. I take now let u equals secant of x squared, because the derivative of secant is secant times tan. This gives me du equals d over dx of secant x squared times dx. This implies du equals secant x squared tangent x squared, and then by chain rule, the derivative of x squared, which is 2x times dx, this dx over here. When we rewrite the integral, this gives us secant x squared tangent x squared 2x dx equals all this secant x squared tangent x squared times 2x dx has become du, and I'm left with only one in my integral. The function whose derivative is 1 with respect to u is u itself. So u plus c is my antiderivative. But because my u is secant x squared, this gives me secant x squared plus c, which is exactly the expression that we had over here. Okay. Now let's move on and write some polynomials as well. And it's slightly different in the sense that we have to make some adjustment using our substitution. Let's evaluate the integral x times x plus 4 to the 700 dx. Okay. Now, nothing seems to be the derivative of the other. But to simplify my work, An appropriate substitution would be that we replace x plus 4 by u, so that I don't have to do any expansion of this 700 powers. So I take let u equals x plus 4. This gives us sorry, something went wrong. Can you hear me? Okay. Now du equals dx. Great, thank you. Because the derivative of x plus 4 is 1. But then what happens to the integral? When I rewrite this, it's x plus 4, 700 dx. This equals, in the orange, x plus 4 is chosen as u to the 700. Dx has become du. It's equal to dx. But I do have this x sitting here. And I can't leave it here because I have to rewrite my whole integral in terms of u. We are changing the variable here. The good thing is that we have an equation that relates our u and x. I'm going to go here and write x equals u minus 4. With this, now this integral becomes u minus 4 u to the 700 du. Okay. Now, multiplying it through, we get u. Okay, my tablet is going finicky. Let's try it again. This equals u 701, 1701 du negative 4 u 700 du. Okay. This equals, by the power rule, u 702 divided by 702 negative 4 u to the 701 divided by 701 plus the constant of integration. Okay. Right, hold on. I have to rewrite this again now. Okay, pardon me for that. Let's do it again. Okay. We made the substitution. Let u equals x plus 4. This gave us du equals dx. And our integral then became x plus 4 to the 700 dx equals x times x plus 4 is u to the 700 du. We went back to our substitution. X equals u minus 4 then. This became u minus 4 u to the 700 du. Okay. This is u 701 negative 4 u 700 du. Okay, this is where we were. Applying the power rule, u 702 divided by 702, 4 u 701 divided by 701 plus the constant of integration. But then we have to go back. U equals x plus 4. So our final answer would be x plus 4 to the 702 divided by 702 negative 4 x plus 4 701 divided by 701 plus the constant of integration. So the difference in this case is that you have a term that you have to deal with using your substitution again. You replace your x plus 4 by u, but then you find your x from your substitution and replace this x at front as well. We have to write the whole integral in terms of our new variable. All right, now some special integrals. And these are 4 special integrals. I'm going to write them as a theorem. The first one is, and I'll give you the results as well, then we'll try to find them as well. Tan x dx equals log natural of secant x plus c. The antiderivative of secant x equals log natural secant x plus tan x plus c. For cotangent x, the integral is log natural of sine x plus c. And finally, for cosecant x, the antiderivative is negative log natural cosecant x plus cotangent x plus the constant of integration. Let's start with tan x. Cotangent would be similar, and we'll do secant, and cosecant will be similar as well. So the antiderivative of tangent x dx. Now, by definition, tan equals sine divided by cosine. Now I make the substitution. Let u equals cos x, because I know its derivative is sine x, which is in the numerator, and I can pair it with dx. This implies du equals negative sine x times dx, taking the differential. Our integral then becomes, or I can write, maybe let's put the negative sign on this side, du equals sine x dx. This gives me integral sine x dx is negative du, and I have taken cos x equal to u. 1 over u times negative 1 du. I can rewrite this as negative 1 over u du. Now the question is, what is the function whose derivative is 1 over u? Or what is the antiderivative of 1 over u? We know that that's equal to negative log natural of u plus c. U equals cos x, negative log natural cos x plus c. I take this negative using the property of the ln, and I'm going to put it over here as an exponent. So log natural cos x negative 1 plus c, and cos to the negative 1, which is 1 over cos, is secant. In the end, I can write log natural of secant x plus the constant of integration. Now cotangent would be similar. Cotangent is cos over sine. You take u equal to sine x instead, and in a similar way, the integral will, you'll get the answer, doing exactly the same process. Now I do the integral of secant. That has a trick with it. Secant x dx. What we do with this is, and we can guess it from our answer as well. We expect a log natural on the right-hand side, and it's the log natural of secant plus tangent. So that means I must have this term, the derivative of this term, secant x plus tangent x, in my numerator. Let's try to construct this. What I'm going to do is, I'm going to write this as secant x. I multiply and divide by this term secant x plus tangent x dx. because I see the log natural of secant x plus tangent x on the right side. Okay. Now all I have to check is, if I take u equals to secant x tan x, is my numerator the derivative of this? If that's the case, you will see the integral will work out. So let u equals secant x plus tangent x. Du would be equal to the derivative of secant x plus tan x times dx. The derivative of secant x is secant times tan. The derivative of tan is secant squared. And then we have dx in the end. If I factor out one secant, I get secant x plus tan x inside the bracket times dx. You see, this is exactly our numerator. So our integral now becomes, let's do that here. This now becomes secant x times secant x plus tan x is du. And we have taken secant x plus tan x as the variable u, which is again log natural of u plus c, and u equals secant x plus tangent x, and lastly, the constant of integration. So in this case, we had to multiply by secant x plus tangent x, and then divide by the same thing as well. Now, as a last example for today, let's take the indefinite integral 18 tangent squared x secant squared x, all divided by 2 plus tan cubed x whole squared dx. This messy expression. Now I have to think about my substitution. What should I take as my substitution? Because the derivative of tan is secant squared, and I see it in the numerator as well, I'm going to start with this substitution, and hopefully it'll at least simplify this integral. So I'm choosing u equals to tangent x with the hope that it'll simplify things for us. Let's do du equals the derivative of tan x times dx. This is secant squared x dx. Great. I rewrite my integral 18 tangent squared x secant squared x 2 plus tan cubed x whole squared dx. This becomes integral 18 tan is equal to u, so u squared secant squared dx is du divided by 2 plus u cubed whole squared du. This is my transformed integral in the variable u. Now at this stage, I don't know what this integral is. But what I do see is that the derivative of 2 plus u cubed is going to be u squared, and I have it in the numerator. I will make one more substitution here. I'll take u equals now, well, I already have a u, so I have to change the variable. I'll check w equals 2 plus u cubed, because I know its derivative is in the numerator. dw would be equal to 3u squared du. Now my integral becomes, it's 18u squared. I'm going to put 6 outside, and 3u squared du is my dw. So dw, 1 divided by w squared is what I'm left with. 2 plus u cubed is my w. I rewrite this as 6 w to the negative 2 dw. Doing the power rule, this is 6 w to the negative 1 divided by negative 1 plus the constant of integration, or negative 6 divided by w plus the constant of integration. We have evaluated the integral now. But now I have to go back step by step. My first substitution was w equals to, second substitution, w equals 2 plus u cubed. This becomes negative 6, 2 plus u cubed, not w, plus c. And then my u was equal to tan x in my very first substitution. Finally, it's -6 divided by 2 tangent cubed x plus the constant of integration. So in this case, I had to do 2 substitutions. I had to do a substitution within a substitution to find the indefinite integral.